Then the other type of exponential function is exponential decay, and the equation for that type is written here, and it looks very similar to the exponential growth equation. What's different is instead of adding, you're subtracting the rate from 1 because you'll have a fraction there. You'll have less than 1. So C is still the initial amount, Y is the future amount, R is the rate in a decimal form, and X is the number of time intervals. So, for example, 3, suppose the number of animals of a certain species in the Amazon is estimated to be 1,250 right now. If this number decreases by 7% each year, find the number of animals in this species in 5 years. Round to the nearest whole number, of course. So, underline some of these numbers here, and that's what we're looking for, the number of animals in the future. So right now there's 1,250. The rate is 0.07, and the time interval is 5 years. Okay, so the future amount is the current amount times 1 minus the rate, because they're decreasing, raised to the time interval of 5 years. So if you want to put that in your calculator just the way it is for a graphing calculator, if you're using scientific, you have to do 1 minus 0.07, raise that to the 5th power, and then multiply by the 1250. So we should get 869.61. And it says round to the nearest whole number, so I will. But if you're looking at exponential decay, you could generally round down. So the whole number here, I'm going to look at the decimal, and it's a 6, so I am going to go up to 870 for the number of animals in the Amazon for this species after 5 years. There's a specific concept of exponential decay called half-life. And that means the amount of time it takes for a substance to be exactly half of the initial amount. So, for example, suppose a radioactive material has a half-life of 32 years. How much of a 700-gram sample remains after 240 years? Round to the nearest tenth of a gram. So, we've got this. It says the half-life is 32 years. So we're going to use that in our time interval. The time interval for half-life is going to be the total time you're looking at for this substance divided by the time it takes to half-life. That will be the total time interval. So in this case, we're looking at a total of 240 years. And it takes 32 years to half-life. And since this is a terminating decimal, I can use 7.5, but if it ended up with a decimal that goes on forever, you don't want to round this. You want to keep this exact. If you can't get an exact decimal, use a fraction. Okay? So this is the time interval, and that will make sure that you are as close to the answer as you need to be without round off error. So we've got the time interval for this decay. And what else do we have? 700 is the original amount. So it does not tell us what the rate is. And it doesn't need to, because we know that in 32 years there'll be half the amount that we started with. So that means that it is a 50% decrease, right? It's a rate of 50% for half-life. And that will be true for all half-lifing. The rate will be 50%. And in the future, you'll have exactly half of what you had to begin with. So what we're solving for here is the future amount. If we start with 700, our rate is 50%, and our time interval here is 7.5. So you can put that in the calculator exactly as it is for graphing calculator. If you've got scientific, you must subtract. That'll be 0.5 raised to 7.5 multiplied by 700. And that answer will be 3.86699, etc. Round to the nearest tenth. So this is where we're rounding. We're going to look over here. And that tells us go up because it's 5 or more. So 3.9 tenth of a gram, so these are grams, of the radioactive material is left after 240 years.